Welcome to AI Paper Podcasts. Today, we're shifting gears a bit. We're moving beyond thinking about AI as just single large models.
That's right. The real cutting edge, especially for complex problems, isn't one giant brain, but, networks of specialized AI agents working together. Agentic AI systems.
Exactly. And that introduces a huge challenge. How do you actually manage these complex networks, especially when you scale up to potentially thousands of agents?
Yeah, the old ways just don't cut it. Static connections, manually figuring out who does what. It breaks down fast. You end up asking basic but critical questions like, okay, who can actually do this specific task?
And what's it going to cost me in terms of resources?
And, crucially, does this agent even meet the policy requirements? Can it legally or ethically touch this data? Those questions become almost impossible to answer reliably at scale with traditional methods.
Which brings us to today's paper. It tackles this exact problem head-on. We're diving into Federation of Agents, FOA, a semantics-aware communication fabric for large-scale agentic AI. This is work out of CERN, actually.
And it's really essential stuff if you're a practitioner thinking about building these large-scale, dependable agent systems.
Okay, so before we get into the weeds, let's do that quick summary for everyone, the kind of thing you might see in a short clip. What's the core takeaway here?
Right, so FOA basically throws out that old static wiring. It replaces it with a dynamic system driven by what agents can actually do. And it does this using three main innovations.
First up, versioned capability vectors, or VCVs. Think of these like super detailed machine-readable profiles for each agent.
Yeah, not just skills, but also cost, policy flags, their core principles. Everything needed to make them searchable and understandable by the system.
Okay, second pillar.
Semantic routing. This is the smart matching part. It uses these efficient search indexes, we'll get into HNSW later, to find the best agent for a job, considering its capabilities, yes, but also cost and absolutely critically policy constraints.
So if an agent isn't allowed to do something based on policy, it just doesn't even get considered.
Exactly. Policy is a hard gate right at the start. And the third piece is smart clustering.
Ah, the refinement step.
Right. Instead of just taking the first answer an agent gives, FOA groups agents working on the same piece of a task. They collaborate, critique each other's work in a structured way for a few rounds, like a mini peer review.
And then the system synthesizes the final result from those refined pieces.
Precisely. And the impact is pretty staggering. On a tough benchmark, HealthBench Hard, FOA got a 13x performance improvement compared to the best single model.
13 times. Okay, that definitely warrants a closer look.
Yeah, it's a huge leap. It really shows the power of structured, dynamic coordination over just throwing more agents at a problem or relying on one big model.
All right, let's dive deeper then. Starting with the absolute core, these versioned capability vectors, the VCVs, what's actually in them? It's more than just a label, right?
Oh, much more. It's a formal structure, a six-tuple, designed to be searched and reasoned about. The first part is the capability embedding. That's a dense vector, basically capturing the agent's core skills semantically.
Like what it's good at, in a nutshell.
Kind of, yeah. Then you have discrete skills, which are more specific, maybe listed skills. They use something like a Bloom filter for this, which is efficient for checking if an agent has a particular skill.
Okay, makes sense. But the next parts seem really geared towards practical deployment.
They really are. Number 3 is resource requirements. This is huge. It encodes quality of service needs things like maximum latency, minimum bandwidth, even energy consumption.
Wait, so the system knows if an agent is running on, say, a low-power device or needs a super fast connection?
Exactly. It makes the system physically aware. If a task needs a response within 50 milliseconds, an agent that typically takes 200 meters just won't be suitable, regardless of its skills. It filters agents based on real-world constraints.
That's critical for edge computing, IoT, anywhere outside a perfectly uniform data center.
Absolutely. And maybe even more critical is the fourth component, policy compliance. These are explicit labels for things like regulatory constraints, GDPR, ITP, whatever, or internal security rules.
The non-negotiables.
The absolute non-negotiables. If the task requires access to sensitive data type X, and the agent's policy flags don't explicitly allow X, it's out. Full stop.
Okay, what else is in the VCV?
There's the Spec Embedding. This captures the agent's, let's call it personality or alignment. It's a semantic summary of its goals, its operating principles, the helpful, harmless, honest criteria that come from things like RLHF.
So it helps match agents whose fundamental goals align with the task.
Right. And finally, just a version counter to keep track of updates to the VCV. Simple but necessary.
So you have these rich VCVs for potentially thousands of agents. How does the central orchestrator, Agent Zero they call it, actually manage and search these efficiently? It can't be just a giant list.
No, definitely not. That's where the sharded HNSW Index comes in. HNSW stands for Hierarchical Navigable Small World.
Okay, HNSW, break that down for us. Why use that specific structure? What's the benefit?
Think of it like creating a super efficient roadmap through the high-dimensional space where these VCV embeddings live. Instead of checking every single agent one by one, which would be incredibly slow.
Linear search, yeah. Terrible at scale.
Right. HNSW builds connections like shortcuts between similar agents. So when Agent Zero gets a task, it can very quickly navigate this graph to find the neighborhood of potentially suitable agents. It gives you sublinear search time, meaning it scales much, much better as your federation grows.
Faster searching. Got it. And how do updates get handled? If an agent learns a new skill or a policy changes, how does its VCV get updated across this distributed index?
They use a Delta Gossip protocol. Instead of every agent shouting its entire VCV every time something changes, which would flood the network.
Right, that sounds like chaos.
Yeah. Delta Gossip means agents just periodically whisper the changes, the deltas, to their neighbors. Those changes then spread efficiently through the network. It's lightweight, decentralized, and avoids communication bottlenecks.
Clever. Okay, so Agent NR uses HNSW to quickly find candidate agents based on their VCVs. Now comes the decision. Which specific agent gets the subtask? Talk us through the scoring function.
This is where all those VCV components come together. The goal is to pick the agent that maximizes the expected utility for that specific subtask. It starts with semantic similarity, how well the agent's capability embedding matches the task description embedding.
Makes sense. Find the agent that knows how to do it.
But, and this is the crucial part we touched on, that similarity score is completely gated by policy compliance. Meaning there's an indicator function, basically a check, is required policy, subtask, a subset of allowed policy agent. If the answer is no, even by one missing permission, the score for that agent instantly becomes 0. Doesn't matter how skilled it is.
Wow, so policy isn't an afterthought, it's baked right into the selection process. That's policy as code at the routing level.
Exactly. It prevents unsafe or non-compliant assignments before they happen. Assuming an agent passes the policy gate, the score is then adjusted further. It gets penalized based on resource gaps, like if it meets the latency requirement, but just barely.
So tighter fits are better.
Right, and it gets boosted by how well the agent's spec embedding aligns with the task's goals. So agents that are not only capable and compliant, but also whose core principles, like being helpful and honest, match the task's intent, get higher scores.
So it's a multi-objective optimization. Capability, cost resources, policy, and alignment.
Precisely. It ensures a holistic best fit, not just optimizing for one dimension.
All right, let's shift to the plumbing. The communication backbone. Given the CERN connection and the need for large-scale, potentially constrained environments, their choice of MQTT5 is interesting. Why MQTT?
It really fits the needs of this kind of asynchronous distributed system. MQTT uses a publish-subscribe model, which is very lightweight. Agent Zero can publish task metadata to a topic, say full meta, and any relevant agent subscribed to that topic will get it. It's efficient for one-to-many communication.
Compared to something like gRPC or REST APIs, which are more point-to-point and synchronous.
Exactly. Synchronous calls would create blocking issues and wouldn't scale well when you have thousands of agents potentially working in parallel. MQTT is designed for low bandwidth, high latency, or unreliable networks, think IoT, or large experimental facilities like CERN's Caffeine platform, where this might be deployed. It's resilient and efficient.
And they use specific topics to organize the communication flow, right?
Yeah, like full meta for tasks, Fortane for persistent VCV updates using that gossip protocol, and Forceult for the final outputs. It keeps things orderly.
Okay, now what about the agents themselves, the agent ones doing the actual work? They aren't just vanilla LMs, are they?
No, they're described as being wrapped around a pre-aligned language model. They often use techniques like GRPO group relative policy optimization to make sure their behavior strictly follows their embedded spec, that E-vector we talked about.
So the spec isn't just for matching, it actually guides the agent's actions.
Yes, it helps them follow instructions properly, decline requests that violate their principles, like unsafe requests, and importantly, signal when they are uncertain. That's the honest part of HHH.
And their skills aren't just theoretical, they have actual tools.
Right. They have tool use controllers. This means they can interact with external resources, perform a vector search, query a SQL database, call an API, And these concrete abilities are what get reflected in the capability embedding and discrete skills parts of their VCV. They can do things.
This structure then enables something pretty sophisticated. Dynamic, collaborative task decomposition. How does that work? Agent Zero doesn't just dictate the plan.
No, and that's a key advantage over simpler systems. When a complex task comes in, Agent Zero doesn't try to guess the perfect multi-step plan up front. Instead, it initiates a cooperative planning phase.
Meaning it asks the agents for help planning.
Essentially, yes. It identifies the top-scoring policy-compliant agents relevant to the overall task. Then, it asks them to propose candidate subtasks and how those subtasks might depend on each other.
So for a big task like review this code base for security flaws, different agents might propose subtasks like scan for known vulnerabilities, analyze data flow for leaks, check dependencies, and map out that, say, dependency checking needs to happen first.
Exactly. Each relevant agent proposes a potential breakdown. And the dependencies. Agent Zero then uses a consensus mechanism to merge these proposals into a single global plan, a directed acyclic graph, or DAG, $0.
A DAG, basically a flowchart where tasks flow in one direction with no loops, showing what needs to finish before the next step can start.
Precisely. And because this DAG is generated collaboratively based on the actual agents available and their expertise, it's much more robust and flexible than a predefined static workflow.
Okay, so we have the plan, the DAG. Agents are assigned subtasks using that scoring function. They generate their initial answers in parallel, and then comes smart clustering.
Yes, the quality control loop. Agent Zero looks at all the agents assigned to the exact same subtask in the DAG and groups them into small clusters, let's say C$, E2, E2, etc.
How does it decide who goes into which cluster? Is it random?
Not at all. It's quite deliberate. They use a hierarchical clustering algorithm based on a similarity matrix. This matrix considers three things.
Okay, what are...
First, the similarity of their core capability embeddings. Are they fundamentally skilled in the same way? Second, the similarity of the preliminary draft answers they just generated. Are they already converging on similar idea, or are their initial takes wildly different?
Interesting. So it looks at both their inherent skills and their initial output. What's the third factor?
Spec embedding overlap. Do these agents share similar core principles and alignment goals? Clustering agents with similar specs helps ensure they're working towards the same definition of a good answer during refinement.
It sounds like it's trying to balance getting diverse perspectives, but maybe not too diverse that they can't even agree on the basics.
That's exactly the trade-off. You want enough diversity to catch errors and improve the result, but not so much that they just argue past each other. The goal is productive peer review.
So once a cluster is formed, what happens inside?
They get their own dedicated communication channel, like a private MQTT topic, full clusters. And then they engage in this iterative refinement loop for a fixed number of rounds, CALE, usually small, like 3 to 5 rounds.
And in each round?
They exchange their current drafts, provide critiques on each other's work, suggest improvements, maybe point out factual errors or areas that lack clarity. It functions like an academic peer review cycle, but automated and very fast.
The paper mentions a potential bottleneck here, though. The communication overhead within a cluster scales quadratically with the cluster size OKC dollars. That sounds expensive. Why accept that quadratic cost?
That's a really important point. Yes, OKC Toyers is computationally more expensive than simpler methods, like just having a leader agent collect answers, which might be linear. But they made a conscious trade-off.
Trading cost for
quality. That intensive back-and-forth peer review process, even with just 3D5 agents, is specifically designed to significantly reduce hallucinations and improve the factual accuracy and coherence of the answer for that subtask. They're paying that quadratic cost within small controlled groups to get a much higher quality output.
So it's a targeted investment in quality where it matters most.
Exactly. And limiting the cluster size dollar to small numbers keeps that quadratic cost manageable in practice. Once the agents in a cluster reach consensus or the dollar rounds are up, they signal task complete.
And then Agent Zero steps back in.
Right. Agent Zero monitors the DAG. As subtasks get completed by their clusters, it moves to the next stage, result synthesis. It traverses the DAG topologically.
Meaning it follows the dependency arrows?
Yep. It makes sure it processes results in the right order. You can't synthesize the final report section before the analysis section it depends on is finished and refined.
And how does it actually combine the refined answers from different subtasks or clusters?
It uses what they call the SYNth operator. This is actually implemented by meta-prompting Agent Zero itself. Based on the DAG structure and the results coming in, Agent Zero figures out how to combine them intelligently.
So it might just concatenate two pieces of text.
Could be simple concatenation, yeah. Or if one cluster's output refines or corrects a predecessor's output, it might perform a rebase operation. If multiple parallel branches of the DAG produce different perspectives on the same point, it might need to merge or summarize them. It's a smart combination step.
Okay, that whole process, VCVs, semantic routing, dynamic DAGs, smart clustering, synthesis, it sounds complex, but the payoff seems huge. Let's talk benchmarks. HealthBench hard.
Right. This is not an easy benchmark. It involves complex, open-ended medical questions, and the answers are evaluated by physicians against detailed rubrics. Very challenging.
And the results for FOA?
The overall score was 0.13. Now, that number itself might not sound amazing, but context is everything. It was a 13x relative improvement over the best single agent they tested, Magema.
13 times better than just using one big specialized model.
Yep, and maybe even more telling, it was 6.5 times better than just running an ensemble of agents without the FOA coordination, without the semantic routing, clustering, and synthesis.
So the coordination fabric itself provides massive value.
Absolutely. It proves that how agents collaborate is critical, especially for tasks needing complex reasoning and integrating multiple pieces of information, which is where the clustering really shone.
Okay, but no system is perfect. What are the current limitations or challenges people should be aware of if they're thinking of implementing something like this?
The authors are pretty upfront about a few things. First, the whole system hinges on good embedding quality. If your VCV capability embeddings aren't accurately reflecting what the agents can do, the semantic routing won't work well. You get a cold start problem for new or poorly described agents.
Garbage in, garbage out for the embeddings.
Pretty much. Second, we already discussed the quadratic communication overhead within clusters. This inherently limits the practical size of the refinement groups, constraining the depth of collaboration on any single subtask.
So it's better for breadth many agents on many tasks than extreme depth on one task.
Generally, yes. And third, security vulnerabilities. While the policy gating helps a lot, it's not foolproof against sophisticated attacks. Think coordinated Sybil attacks where many fake agents collude, or agents deliberately misrepresenting their capabilities in their VCVs.
How does FOA handle trust and verification then?
It does maintain auditable provenance trails, so you can see which agents contributed to which part of the final result. That helps with forensics. But fundamentally, there's still a degree of trust required in the VCV declarations themselves.
Which leads nicely into future work. Where does this research point next? What should people be exploring?
Three main directions stand out. One is making the routing even smarter. Instead of fixed rules, using reinforcement learning to create adaptive routing controllers. These could dynamically adjust how it weighs cost versus semantic match, or change thresholds based on network load or task priority.
More dynamic optimization. What else?
Expanding communication beyond the cluster boundary. Developing protocols for cross-cluster knowledge sharing. Imagine insights gained during refinement in one cluster being efficiently shared with another cluster working on a related subtask elsewhere in the DAG.
That could lead to even better global solutions. And the third area?
Tackling that trust issue head-on. Exploring the integration of things like zero-knowledge proof systems or trusted execution environments, PEs.
Okay, ZKPs or PEs, how would that help here?
It would allow for verifiable capability attestations. An agent could cryptographically prove that it meets certain policy requirements or possesses certain computational resources without having to reveal its underlying model or proprietary data. It shifts from, trust me, my VCV is accurate, to, here's mathematical proof. That's a potential game changer for security and trust in large federations.
So wrapping up, FOA really feels like a significant step forward. It moves multi-agent coordination from static, manual setups to something dynamic, searchable, and aware of real-world constraints like cost and policy.
Yeah, it provides a standardized communication fabric with MQTT, introduces these clever collaborative refinement clusters that demonstrably boost quality, and crucially, it weaves governance and resource awareness right into the core orchestration logic.
Which brings us to our final thought, something for you, the listener, particularly if you're building or thinking about these systems. FOA gives us technical mechanisms for policy enforcement and audit trails. But think about this. In these massive autonomous federations where the exact path of execution, which agents get chosen, how tasks are broken down, how they're refined, is decided dynamically by algorithms optimizing for capability, cost, and policy. How do we establish clear, understandable accountability?
That's the big question. When things go wrong, who or what is ultimately responsible?
Exactly. When the decision-making path is emergent and optimized, not strictly predefined by a human, tracing liability and ensuring ethical operation becomes incredibly complex. Moving beyond technical feasibility to robust governance and accountability frameworks for these dynamic federations, that feels like the next major frontier we need to cross.